The Yarkovsky effect is a subtle and persistent force that operates on celestial bodies, especially those that are smaller and less massive than planets. It is a force born from the interaction between a body's rotation and the heat it absorbs from the sun. This effect, though infinitesimally small, can gradually and powerfully alter the orbits of asteroids and other small objects in space. Over long periods, these tiny shifts in trajectory can become significant, leading to changes in the paths of objects moving through the solar system. Unlike more familiar forces like gravity, which pull objects toward one another, the Yarkovsky effect is a result of the way a rotating body radiates heat into space. The warmth absorbed by a body during the day, and how it is re-emitted during its rotation, affects the motion of the object in space. In this section, we explore how this tiny force, so often overlooked, can silently push worlds across the cosmos. The solar system, as vast as it is still shaped by forces that go unnoticed by the naked eye. And the Yarkovsky effect is one of the most fascinating of these forces. In the absence of a detailed understanding, it may seem that celestial bodies follow a fixed path determined solely by gravity. However, the reality is that small factors like the Yarkovsky effect acting over the course of millions or even billions of years can alter the paths of asteroids, comets, and other small bodies in profound ways. The simplest way to understand the Yarkovsky effect is to think of it in terms of a rotating object that absorbs heat from the sun. As it turns, the object is not only absorbing heat, but also releasing it, and the way it releases this heat affects its movement through space. The warmth of the object during the day is re-emitted as the body rotates, but the heat is not uniformly distributed across its surface. This uneven distribution of thermal radiation generates a force that pushes the object slightly in the direction of its rotation. The result is that over time, this force can cause the body to drift ever so slightly from its original course. While the Yarkovsky effect is too small to have an immediate impact on a body's motion, it is persistent. Over the course of millions of years, even a tiny push can accumulate into a significant deviation from the original path. This shift is not just a theoretical concept, but has been observed in many instances in the solar system. The impact of the Yarkovsky effect becomes more noticeable on smaller bodies like asteroids, which lack the immense mass of planets, and therefore feel the effect more strongly. Larger bodies like planets are much less susceptible to this force, as their greater mass and slower rotation make any changes in their orbit negligible. However, for the smaller objects that populate the asteroid belt and beyond the Yarkovsky effect can be a game changer. It's a force that, while subtle, shapes the movement of bodies across vast stretches of space, influencing not just their motion, but their eventual fate. Asteroids, for example, are not static objects. They are constantly moving and changing their positions within the solar system. While most of these movements are driven by gravitational interactions with planets and other bodies, the Yarkovsky effect adds a layer of complexity to their motion. A small asteroid in the outer reaches of the solar system may appear to be following a stable orbit, but over the course of millennia, the Yarkovsky effect can slowly shift its trajectory, pushing it into a different orbit. This movement, although seemingly insignificant at first, can eventually bring the asteroid closer to the inner solar system, or even on a collision course with Earth. One of the key features of the Yarkovsky effect is its unpredictability. While we can measure the amount of heat that an object absorbs and re-emits, and we can model its rotation, the actual outcome of the Yarkovsky effect on a body's trajectory is difficult to predict. It depends on a variety of factors, including the object's size, shape, surface composition, and rotational speed. Some asteroids experience a stronger Yarkovsky effect than others, and the way they respond to this force can vary widely. The unpredictability of the Yarkovsky effect makes it both a fascinating and challenging area of study for scientists. It also makes the Yarkovsky effect an important consideration in planetary defense. As we look for ways to mitigate the threat of asteroid impacts on Earth, understanding how small forces like the Yarkovsky effect can influence asteroid orbits is crucial. If we can predict how an asteroid's trajectory may be altered over time, we may be able to develop strategies to redirect the asteroid if necessary. In addition, the Yarkovsky effect is a crucial factor to consider when studying the long-term evolution of the solar system. Over billions of years, the positions of asteroids, comets, and other small bodies have been influenced by the Yarkovsky effect, slowly reshaping the structure of the solar system. This process continues today, with the Yarkovsky effect playing a role in the movement of asteroids and other bodies in the asteroid belt, Kuiper belt, and Oort cloud. As we learn more about the Yarkovsky effect, we gain insights not only into the motion of individual bodies, but into the broader dynamics of the solar system. This understanding has implications for a variety of fields, from planetary defense to the study of planetary formation and the evolution of small bodies in space. While the Yarkovsky effect operates on a small scale, its long-term consequences are anything but insignificant. The silent push of this tiny force shapes the motion of worlds, guiding them across the vastness of space. It is a force that has the potential to alter the fate of asteroids, comets, and even planets, though its impact may not be immediately visible. In the grand scheme of the solar system, the Yarkovsky effect is just one of many forces at play, but it is a reminder of how even the smallest influences can accumulate over time to create significant change. The Yarkovsky effect arises from the interplay between an object's rotation and the absorption and emission of heat. While this may seem like an abstract concept at first, it's the core principle that governs the subtle forces pushing asteroids and other celestial bodies across the vast reaches of space. Heat in this context is not simply about temperature. It involves the way energy from the sun interacts with a rotating object, causing it to absorb heat during its daylight cycle, and then re-emit that energy in the form of thermal radiation as it turns. This process, though seemingly inconsequential, creates a tiny but persistent force that gradually alters the object's velocity in its orbit. The Yarkovsky effect operates through a fundamental principle of thermodynamics. When a rotating body absorbs heat, it doesn't release it in a uniform manner. The surface temperature of the object varies depending on its exposure to sunlight. The sunlight warms the body during the day, but as the object rotates, it cools on the night side, radiating heat back into space. This discrepancy in the temperature distribution across the body generates a force often described as a thermal recoil effect. The re-emission of heat is not isotropic. That is, it doesn't radiate evenly in all directions. The object, because it is rotating, radiates more heat in the direction opposite its rotation. The net result of this process is a small but continuous force that causes the object to move slightly away from its original trajectory. To visualize this effect, imagine a rotating sphere exposed to the sun. The side of the sphere facing the sun heats up, while the opposite side cools as it moves into the shadow. The cooling side radiates heat away from the object, and the uneven distribution of this thermal radiation creates a small force that pushes the object in the direction of its rotation. Over time, this force compounds, and despite being incredibly small, it can gradually change the body's orbit. This process is particularly effective when the body is small and light, such as an asteroid. Larger bodies like planets do not experience a noticeable Yarkovsky effect because their mass and slower rotation mean that any changes in their orbits would be insignificant in comparison to the other forces acting upon them. The effect is most pronounced on smaller bodies, where the tiny thermal recoil can accumulate over millions of years, pushing the body into new trajectories. When it comes to the Yarkovsky effect, the size, shape, and rotation rate of the object are key factors in determining how much the force will influence its orbit. For example, an asteroid with a rapid rotation and a high thermal inertia will experience a stronger Yarkovsky effect than one with a slow rotation or low thermal conductivity. These factors create a complex relationship between the object's characteristics and the resulting motion. The role of the sun in this process cannot be overstated. The sun is the source of the heat that drives the Yarkovsky effect. The intensity of the solar radiation that strikes the object is a function of both its distance from the sun and its surface properties. The amount of heat an asteroid absorbs depends on its reflectivity or albedo, as well as its surface texture. Darker surfaces absorb more heat than lighter ones, which can lead to a greater Yarkovsky effect. Furthermore, the rotation of the object itself plays a significant role in how heat is distributed and how it is released. An object with a faster rotation will re-emit heat more quickly than one with a slower rotation, increasing the impact of the Yarkovsky effect. While this process is slow and subtle, its cumulative effect over time can have profound consequences. Over millions or even billions of years, the continuous push of the Yarkovsky effect can alter the orbits of asteroids enough to change their positions in the solar system. This can bring them closer to the Earth, or alter their trajectory toward other planets. The power of heat and rotation, though seemingly a trivial influence in the short term, becomes a driving force of cosmic change when considered on timescales that span millions of years. One of the most important implications of the Yarkovsky effect is its ability to alter the paths of asteroids in ways that may be hard to predict. The interaction between the object's heat absorption emission and rotation rate introduces a level of unpredictability in the way asteroids move. While astronomers can model the Yarkovsky effect, they often face difficulties in predicting the exact impact it will have on an object's orbit due to the complex and varying factors involved. For instance, the exact distribution of heat across an asteroid's surface depends on its size, shape, and the material it is made of, which can be difficult to determine. However, despite these uncertainties, the influence of the Yarkovsky effect is now widely recognized and has been observed in many instances. It is a crucial consideration when studying the long-term evolution of asteroids and other small bodies in the solar system. As scientists continue to observe asteroids and monitor their movements, the role of the Yarkovsky effect will only become clearer, adding another layer of complexity to our understanding of how small forces shape the solar system. The understanding of the Yarkovsky effect also has practical implications in planetary defense. With the increasing focus on monitoring near-Earth objects, scientists are using knowledge of the Yarkovsky effect to help predict the future trajectories of potentially hazardous asteroids. By taking into account how small forces can slowly alter the orbits of these objects, we can better understand their long-term paths and assess whether they pose a threat to Earth. As we continue to refine our models and improve our observation techniques, we will be able to make more accurate predictions about the movement of asteroids and the potential risks they may pose. The Yarkovsky effect in this context becomes a key factor in the ongoing effort to protect Earth from asteroid impacts. The power of heat and rotation is a reminder that even the smallest forces acting over vast timescales can have an immense impact. The Yarkovsky effect, though invisible and seemingly insignificant, is one of the many subtle forces shaping the universe. While it might not be immediately obvious, its influence is far-reaching, altering the courses of celestial bodies across the solar system and beyond. The slow, persistent push of this force exemplifies how even the tiniest influences, when accumulated over time, can change the direction of worlds. The Yarkovsky effect, while initially discovered in relation to the motion of asteroids, extends far beyond the confines of our planet. Earth, with its vast oceans, thick atmosphere, and active tectonics, is largely immune to the subtle push of this effect. The dynamics of our planet are driven by far stronger forces such as the Moon's gravitational pull and the Sun's constant gravitational influence. However, the Yarkovsky effect becomes much more pronounced when applied to smaller celestial bodies, particularly asteroids. These objects, which inhabit the asteroid belt between Mars and Jupiter and stretch outward toward the Kuiper belt and beyond, are not as heavily influenced by external forces. They are instead primarily shaped by the interaction of their own rotation and the heat they absorb and re-emit. It is on these small bodies that the Yarkovsky effect has a significant observable impact. While the basic principle of the effect remains the same regardless of the body being studied, the way it manifests is different for each object depending on its size, shape, rotation rate, and surface composition. Asteroids, unlike planets, are not shielded by thick atmospheres or protective magnetic fields. As such, they are more exposed to the full intensity of solar radiation, which directly affects the way they absorb and release heat. Because of this, the Yarkovsky effect has been a key player in altering the orbits of these small rocky bodies. The movement of asteroids is often unpredictable, and this unpredictability is heightened by the Yarkovsky effect. In a practical sense, the force operates as a slow, cumulative push, causing small changes in the asteroid's orbit over long periods. These tiny shifts can add up, eventually leading to significant alterations in the asteroid's trajectory. In some cases, this movement can even send an asteroid on a path toward Earth, or cause it to veer toward other planets. Asteroids, especially those that are irregularly shaped or have varying surface properties, are particularly sensitive to the Yarkovsky effect. Their irregular shapes cause uneven heat distribution across their surfaces, leading to an increased thermal recoil force. For example, an asteroid with a lopsided shape may absorb and release heat in a way that accentuates the Yarkovsky effect, pushing it on a path that diverges from what might have been predicted based purely on gravitational forces. This irregularity, combined with differences in surface composition, can make it difficult to predict the precise effect the Yarkovsky force will have on any given asteroid. The influence of the Yarkovsky effect on asteroids has been observed in several key cases. One such example is the asteroid 243 Ida, a relatively small body that orbits between Mars and Jupiter. Observations of Ida's orbit show that the Yarkovsky effect has played a role in slowly altering its trajectory. This alteration is subtle, but consistent, and over millions of years it could potentially have a significant impact on its path. The changes in orbit caused by the Yarkovsky effect are generally small, but they are continuous. Over time, these small adjustments can lead to significant shifts in the asteroid's orbit, moving it away from its original course, or even altering the size of its orbit. This slow but steady change has the potential to bring asteroids into the inner solar system, or even alter their paths to the point where they may cross Earth's orbit. In addition to irregular shapes, the rotation speed of an asteroid plays a critical role in determining how strongly it will be affected by the Yarkovsky effect. A faster rotating body will experience a more pronounced Yarkovsky effect because it radiates heat more quickly than a slower rotating body. Faster rotation means that the heat that has been absorbed during the day is released more rapidly during the night phase, creating a greater disparity between the warm and cool sides of the object. This increase in thermal recoil can amplify the push caused by the Yarkovsky effect, leading to a greater deviation in the asteroid's orbit. In contrast, an asteroid with a slow rotation may experience a weaker Yarkovsky effect, as it takes longer for the heat to be redistributed across its surface. Thus, the rotation rate of an asteroid can be a determining factor in how strongly the Yarkovsky effect influences its orbit. Similarly, the surface composition of the asteroid plays a role in its susceptibility to the Yarkovsky effect. An asteroid with a dark surface, for instance, absorbs more solar radiation than a lighter-coloured asteroid, which increases the amount of heat it retains. As a result, darker asteroids may experience a stronger Yarkovsky effect, causing them to move more significantly over time. Lighter asteroids with higher albedo reflectivity may absorb less heat, and therefore feel the effects of the Yarkovsky force to a lesser degree. These differences in surface properties provide scientists with clues about how asteroids will behave over long timescales. In terms of predicting asteroid movement, understanding the Yarkovsky effect is critical for astronomers. By measuring the temperature distribution across an asteroid's surface and tracking its rotation, scientists can model the potential changes in its orbit. This predictive capability is important not just for understanding how asteroids move, but also for assessing the potential risks they pose to Earth. A slight shift in an asteroid's path due to the Yarkovsky effect, although undetectable over short periods, could lead to a collision with Earth over the course of millions of years. This makes it essential for planetary defense initiatives to account for the Yarkovsky effect when assessing the risks posed by near-Earth objects, NEOs. The relationship between Earth and asteroids, especially those in the asteroid belt, is also influenced by the gravitational pull of nearby planets such as Jupiter. These gravitational interactions can alter an asteroid's orbit significantly, sometimes in a manner that works in concert with the Yarkovsky effect, further pushing the asteroid toward the inner solar system. When these forces combine, they can result in a phenomenon known as a gravitational Yarkovsky resonance, in which the gravitational influence of a planet amplifies the effects of the Yarkovsky force, accelerating the movement of the asteroid in space. This interplay between gravity and the Yarkovsky effect is another layer of complexity that astronomers must consider when modelling asteroid trajectories. The Yarkovsky effect is not just a theoretical concept, it has practical consequences. As scientists continue to monitor asteroids and comets, the influence of this subtle force becomes an essential part of understanding how these bodies evolve over time. Whether for planetary defense or space exploration, the Yarkovsky effect is a reminder of how small forces can have large-scale implications. By understanding how heat absorption and rotation work together to subtly alter the paths of asteroids, scientists are gaining a deeper understanding of how our solar system operates. And as we continue to study these small bodies, the role of the Yarkovsky effect will only grow in importance, shedding light on the dynamic and ever-changing nature of the solar system. The Yarkovsky effect, though imperceptible in the short term, orchestrates a slow, constant movement of small bodies through space. As asteroids and other celestial objects absorb heat from the Sun and emit it as they rotate their orbits gradually shift. This subtle yet continuous change in velocity leads to a dance of cosmic proportions, one that takes place over millions of years. While gravity might dominate the movements of larger celestial bodies like planets, the Yarkovsky effect plays a significant role in the evolution of smaller bodies. Over time, these tiny forces, which seem insignificant on their own, can accumulate into vast changes in the paths of asteroids, turning what once seemed like stable orbits into unpredictable trajectories. This is the dance of the rocks, a slow, gentle motion that shifts the orbits of asteroids and comets in ways that might one day have profound consequences. The impact of the Yarkovsky effect is not felt immediately, but it builds incrementally, making the movement of asteroids a gradual and ongoing process. Over the course of millions of years, the Yarkovsky effect has altered the orbits of many asteroids in the solar system. These changes are not dramatic on a human timescale, but over geological periods, the cumulative effect is substantial. Even the slightest change in an asteroid's velocity, if sustained over enough time, can send the object on a completely new path. This constant, persistent push, though imperceptible day to day, is what drives the gradual shift in orbits, creating a dynamic and evolving solar system. While most objects in the solar system, such as planets and moons, follow stable, well-defined orbits, asteroids are much more fluid. Their orbits are influenced not only by gravitational interactions with other objects like planets and the Sun, but also by the subtle long-term effects of the Yarkovsky force. Over time, these forces can combine, creating a complex web of interactions that shapes the future trajectories of asteroids. This dance is not random, but follows a predictable path once the relevant factors such as the size rotation and surface composition of an asteroid are understood. When multiple forces such as gravity and the Yarkovsky effect act in concert, they can create powerful resonances that dramatically alter an asteroid's orbit. These resonances can push an asteroid into different orbital zones, sometimes even altering its position within the solar system. The unpredictability of these dances, while a fascinating part of the dynamics of small bodies, is also one of the reasons why the Yarkovsky effect has significant implications for planetary defense. If an asteroid's orbit is altered enough by the Yarkovsky effect, it could end up crossing Earth's orbit, potentially leading to a collision. While the likelihood of such an event occurring is low, the reality is that over long timescales, the influence of small forces like the Yarkovsky effect can make a difference. The Yarkovsky effect is not the only force in play, but it adds an important layer of complexity to the dynamics of asteroids. The interaction of heat radiation, an asteroid's rotation, and the gravitational influences of nearby planets all contribute to the overall dance of the rocks, guiding them on their journey through the solar system. This dance is not always predictable, especially when the asteroids in question have irregular shapes or other surface features that affect their heat absorption and re-emission. These variations introduce an element of unpredictability, making the path of even the smallest asteroids a topic of ongoing research and observation. To better understand how the Yarkovsky effect alters the orbits of asteroids, scientists use sophisticated modelling techniques. These models take into account not just the gravitational forces at play, but also the thermal characteristics of the objects involved. By understanding how heat is absorbed and released, and by tracking the rotational properties of asteroids, scientists can predict how the Yarkovsky effect will influence their orbits over time. This predictive capability is essential for understanding the long-term movements of asteroids and for assessing their potential risks. The dance of the rocks shaped by the Yarkovsky effect is not just a theoretical idea, but something that is observed in real time. Asteroids such as 16273, Ryugu, and 26443 Itokawa have been studied closely, revealing how their orbits are influenced by small, subtle forces. By tracking the positions of these asteroids and measuring their rotation, scientists have been able to confirm that the Yarkovsky effect plays a significant role in their orbital evolution. The more we study these bodies, the clearer it becomes that even the tiniest forces can have large-scale effects. This is especially true in the case of asteroids which lack the protective atmospheres and massive sizes of planets, making them more vulnerable to the Yarkovsky effect. Even small changes in their orbits over vast periods of time can result in significant shifts in their trajectories. As scientists continue to study these phenomena, they are able to refine their models and make more accurate predictions about the future movements of asteroids. By understanding the dance of the rocks, they can anticipate how asteroids will move over the coming millions of years and assess the likelihood of any potential collision with Earth. The constant evolution of asteroid orbits is a reminder of the dynamic nature of the solar system. While the planets may seem stable and unchanging, the small bodies that populate the solar system are in a constant state of flux. The dance of the rocks is a silent, slow-moving process, one that may not be noticed on a day-to-day basis, but that has profound implications for the future. Even the most stable orbits are not immune to change. The Yarkovsky effect ensures that no asteroid, no matter how small or seemingly insignificant, is bound to follow the same path forever. The dance of the rocks, shaped by the subtle forces of heat and rotation, ensures that the solar system remains a dynamic and ever-evolving place. The Yarkovsky effect, in its quiet persistence, is a powerful force shaping the fate of celestial bodies. Over time, the paths of asteroids will continue to shift, pushed along by this tiny invisible force, guiding them across the vast reaches of space, in a slow and steady dance that will carry them far beyond where they began. The Yarkovsky effect, while seemingly subtle in its immediate impact, does not act in isolation. It is influenced and often counterbalanced by other forces that shape the motion of celestial bodies. A celestial object, whether an asteroid or a comet, is rarely subject to only one force at a time. Instead, it is engaged in a cosmic tug-of-war between different forces that work together, sometimes in harmony, and other times in opposition to alter the object's trajectory. At the forefront of this tug-of-war is gravity, the most dominant force in the solar system. Gravity is the force that keeps the planets in orbit around the Sun, governs the motion of moons around planets, and influences the paths of asteroids and comets. The gravitational pull of large bodies, particularly the Sun and the planets, is the primary factor governing the motion of most objects in space. However, even gravity's influence is not absolute, and it is here that the Yarkovsky effect plays its role. While gravity dictates the general shape of an object's orbit, it is the Yarkovsky effect that can alter the finer details, nudging an asteroid's trajectory and causing small deviations that accumulate over long periods. In this way, the Yarkovsky effect acts as a counterforce to the more dominant gravitational pull, shifting the asteroid's path ever so slightly. Over millions of years, these small shifts can cause an object to drift far from its original course, potentially resulting in a collision or a change in orbit that brings the asteroid closer to Earth or another planet. The relationship between the Yarkovsky effect and gravity is complex. The two forces interact in ways that are difficult to predict. For example, in some cases, the gravitational pull of a planet, particularly a large one like Jupiter, can amplify the Yarkovsky effect, creating a resonance that further shifts the asteroid's orbit. This interaction is known as a gravitational Yarkovsky resonance, and it occurs when the gravitational forces from a planet synchronize with the Yarkovsky effect, reinforcing the effect's influence on the asteroid. The result is a much more pronounced change in the asteroid's trajectory. Jupiter, due to its massive size and strong gravitational influence, plays a key role in shaping the orbits of many asteroids. The gravitational forces from Jupiter can perturb the orbits of nearby objects, pushing them into different orbital paths. When combined with the Yarkovsky effect, this gravitational influence can have a dramatic impact on the trajectory of asteroids, sometimes causing them to move toward the inner solar system or toward Earth's orbit. The gravitational tug-of-war is not limited to interactions with planets. The Sun itself, with its powerful gravitational pull, also plays a significant role in shaping the orbits of asteroids and other small bodies. While the Sun's gravity keeps objects like asteroids in their general orbits, the Sun's radiation pressure and the Yarkovsky effect combine in ways that alter the trajectory of these objects. The Sun's radiation in particular is a force that can push objects away from the Sun, and in combination with the Yarkovsky effect, this can create a shift in an asteroid's orbit that is distinct from what would be predicted by gravitational forces alone. The forces involved in this cosmic tug-of-war are not always straightforward or predictable. The combination of the Yarkovsky effect, gravity and solar radiation pressure can lead to complex orbital resonances, where the interactions between different forces cause the asteroid to oscillate between different orbital paths. These resonances can create patterns of motion that are difficult to anticipate, as the small adjustments made by the Yarkovsky effect can build up over time, leading to unexpected changes in an object's orbit. While the Yarkovsky effect is often considered a small force compared to gravity, its long-term influence can be substantial, especially when combined with other forces acting on an asteroid. The tug-of-war between these forces is a defining feature of the dynamics of the solar system. It is through these interactions that the orbits of asteroids, comets, and other small bodies are shaped, sometimes leading to dramatic changes in their trajectories. These changes are not limited to the movement of asteroids. The gravitational tug-of-war extends to comets as well. Comets, which are composed of ice dust and rocky material, are particularly vulnerable to the Yarkovsky effect. As comets approach the Sun, they absorb heat and begin to vaporize, creating a tail of gas and dust that can be pushed by the Yarkovsky effect. The combination of the Sun's radiation and the comet's rotation can alter the shape of the comet's orbit, potentially changing its trajectory and path. Over time, the Yarkovsky effect can influence the direction in which the comet's tail is pointed, affecting the overall motion of the object. Like asteroids, comets are not immune to the tug-of-war between gravity and the Yarkovsky effect. The gravitational pull of the Sun, as well as the gravitational influence of planets, interacts with the small forces of thermal radiation and rotation, creating complex orbital dynamics. These interactions can result in dramatic changes in the path of a comet, sending it into new regions of the solar system or altering its timing of arrival at Earth. The interplay between the Yarkovsky effect and gravitational forces is a crucial consideration for planetary defense. As scientists track near-Earth objects, they must take into account not just the gravitational influences of planets and the Sun, but also the subtle but persistent effect of the Yarkovsky force. The Yarkovsky effect's ability to alter the trajectory of asteroids and comets over time means that even objects that currently pose no threat to Earth could over millions of years move into dangerous proximity. This understanding has led to a growing interest in planetary defense strategies aimed at mitigating the potential risks posed by near-Earth objects. By accounting for the cosmic tug-of-war between gravity, solar radiation, and the Yarkovsky effect, scientists can better predict the long-term trajectories of asteroids and comets, allowing us to anticipate potential hazards. The forces involved in this cosmic struggle, though small on a short-term scale, accumulate over vast timescales. The Yarkovsky effect is a reminder that even the most minor forces can lead to substantial changes in the paths of objects in space. In the grand sweep of the solar system, the tug-of-war between forces like gravity, radiation, and thermal effects is a defining feature of the dynamics of the universe. And it is through this interaction that the future trajectories of asteroids, comets, and even planets will continue to evolve. The Yarkovsky effect, though a subtle force, has profound implications for the movement of asteroids and other small celestial bodies. Despite its small size, scientists have developed innovative methods to track and measure the changes it induces in an asteroid's orbit. This process involves detecting movements that are imperceptible to the naked eye, but when examined over long timescales reveal significant shifts in an object's trajectory. Tracking the Yarkovsky effect is a challenge for astronomers, as the changes it causes are gradual and its influence is often masked by the much stronger gravitational forces at play. The first step in detecting this force is identifying objects that are likely to be affected by it. Asteroids, especially those that are small, irregularly shaped, and have fast rotations, are the prime candidates for Yarkovsky-induced orbital shifts. Large planets and moons, with their massive sizes and slow rotations, experience negligible effects from this force. Therefore, most of the research surrounding the Yarkovsky effect focuses on small bodies in the asteroid belt and beyond. By measuring the orbits of these bodies with precision, scientists can detect even the slightest changes in their paths. One of the most commonly used methods for tracking the Yarkovsky effect is radar observation. Radar systems can bounce radio waves off an asteroid, allowing scientists to measure its position and velocity with remarkable accuracy. This method can be used to track the asteroid's orbit over time, revealing any deviations from its expected path. As the Yarkovsky effect causes the object to slowly shift its orbit, these small changes can be detected by radar, even if the movement is imperceptible over short periods. Over time, repeated radar measurements can help astronomers calculate how the Yarkovsky effect is influencing the object's trajectory. Another powerful tool for tracking the Yarkovsky effect is optical observation. Telescopes, both ground-based and space-based, can be used to monitor the position of asteroids as they move across the sky. By measuring the asteroid's position relative to distant stars, astronomers can track its movement with high precision. Optical observations are especially useful for detecting the positions of asteroids over long periods, as they can provide continuous data that can be analysed for subtle orbital shifts. Additionally, the brightness of an asteroid can provide clues about its surface properties and rotation. Asteroids with irregular shapes, for example, may appear brighter or dimmer as they rotate due to the way sunlight is reflected from their surfaces. This variation in brightness can be used to determine the object's rotation rate, which is crucial for calculating the Yarkovsky effect. By combining radar and optical observations, scientists can build a comprehensive picture of an asteroid's movement, helping them to pinpoint the influence of the Yarkovsky effect. This data can then be used to refine models of the asteroid's orbit and predict its future path. However, detecting the Yarkovsky effect is not without challenges. The force itself is incredibly small, and its effects are slow to accumulate. In many cases, the influence of the Yarkovsky effect is so subtle that it may take decades or even centuries before the changes in an asteroid's orbit become noticeable. Moreover, the Yarkovsky effect is just one of many factors that influence an asteroid's movement. Gravitational interactions with planets' solar radiation pressure and other forces all contribute to the object's trajectory. Isolating the Yarkovsky effect from these other influences is a complex task. One approach to overcoming this challenge is to study asteroids that are well understood and have been observed over long periods of time. By analysing the orbits of these objects in great detail, scientists can identify the contributions of various forces, including the Yarkovsky effect. This method allows astronomers to tease apart the influence of the Yarkovsky effect from other forces and gain a clearer understanding of its role in shaping an asteroid's path. Another method for detecting the Yarkovsky effect is through computer modelling. By inputting data on an asteroid's size, shape, rotation rate, and surface properties, scientists can simulate how the Yarkovsky effect should influence its orbit. These models can be used to predict how the asteroid will move over time, providing a benchmark for comparison with observational data. If the model's predictions align with the observed orbital shifts, this provides strong evidence that the Yarkovsky effect is at play. However, modelling the Yarkovsky effect is far from straightforward. The complexity of the interactions between heat absorption, emission, and rotation makes it difficult to create accurate models that can account for all the variables at play. Factors such as the asteroid's surface texture, albedo, and irregular shape can all affect the way heat is redistributed, making it challenging to predict exactly how the Yarkovsky effect will influence its orbit. Despite these challenges, the combination of radar optical observations and computer modelling has allowed scientists to make significant strides in understanding the Yarkovsky effect. By tracking asteroids and comets over long periods of time, astronomers have been able to observe firsthand how the Yarkovsky effect shapes their motion. As our observational techniques improve and our models become more refined, we will be able to track the Yarkovsky effect with even greater precision. This will have important implications for planetary defense, as understanding how small forces like the Yarkovsky effect can influence asteroid orbits will help scientists better predict potential hazards to Earth. In addition to its practical applications, the study of the Yarkovsky effect provides valuable insights into the long-term evolution of the solar system. As we track the movement of asteroids and other small bodies, we gain a deeper understanding of the forces that shape the solar system's structure. The Yarkovsky effect is just one example of how small forces acting over vast timescales can have significant consequences for the motion of celestial bodies. By continuing to track and study these objects, scientists are uncovering the intricate dynamics that govern the movement of small bodies in space. These insights not only enhance our understanding of the solar system, but also provide crucial information for our ability to monitor and protect our planet from potential threats. Among the many asteroids studied for the effects of the Yarkovsky force 243, Ida stands out as a significant example. This relatively small asteroid located in the asteroid belt between Mars and Jupiter offers a glimpse into the subtle long-term influences of the Yarkovsky effect on an object's orbit. At first glance, 243 Ida may appear to follow a predictable path around the Sun governed by gravitational interactions with other celestial bodies. However, closer examination reveals that the Yarkovsky effect plays a role in shifting its trajectory, gradually altering its orbit in ways that can be traced over time. 243 Ida is not alone in its vulnerability to the Yarkovsky effect. Many asteroids in the asteroid belt exhibit similar behaviours. However, Ida's relatively large size and well-documented orbit make it an ideal candidate for studying the long-term influence of this small persistent force. Discovered in 1884, 243, Ida was studied in detail by NASA's Galileo spacecraft, which flew past the asteroid in 1993. The spacecraft's observations of the asteroid's orbit revealed small deviations from its expected path deviations that could be attributed to the Yarkovsky effect. These subtle changes, although imperceptible over short periods, became apparent when the asteroid's position was tracked over many years. The most important finding was that Ida's orbit had been slowly shifting in response to the re-emission of heat from its surface. As the asteroid rotated, the uneven distribution of heat caused by the Sun's radiation created a tiny force that pushed the asteroid in the direction of its rotation. This shift was small but continuous, building over time and altering the shape of the asteroid's orbit. The Yarkovsky effect was not the only factor at play in Ida's orbital evolution. Gravitational interactions with nearby planets, particularly Jupiter, also contributed to the asteroid's motion. However, the Yarkovsky effect's role in the long-term changes in Ida's orbit was significant, offering a clear example of how small forces can alter the paths of celestial bodies. In Ida's case, the Yarkovsky effect served as a subtle but persistent influence on its orbit, one that worked in concert with the gravitational forces from other objects in the solar system. This interaction between forces is a key feature of the dynamics of small bodies in space. By analysing the movement of Ida over a period of time, scientists have been able to better understand how the Yarkovsky effect operates on asteroids and other similar objects. The study of Ida has also provided valuable insights into the broader implications of the Yarkovsky effect for planetary defence. While Ida is not a near-Earth object and poses no immediate threat to Earth, its case demonstrates how small forces acting over long periods can influence the movement of objects in the solar system. The Yarkovsky effect, when combined with gravitational forces, can lead to significant changes in an asteroid's orbit, potentially altering its path toward Earth or other planets. As scientists continue to track and study asteroids like 243 Ida, they can refine their understanding of how the Yarkovsky effect impacts orbital dynamics. This knowledge is essential for assessing the risks posed by near-Earth objects, which are subject to similar forces. In particular, understanding how the Yarkovsky effect can alter an asteroid's path over millions of years allows scientists to predict the future trajectories of these objects. By tracking the movements of known asteroids and monitoring their rotations, scientists can anticipate how the Yarkovsky effect will influence their orbits. This is especially important when it comes to planetary defense, as even a small shift in an asteroid's orbit could over long periods result in a collision with Earth. By studying objects like 243, EDA astronomers can develop more accurate models for predicting the movement of other asteroids in the solar system, including those that pose potential risks to Earth. The case of 243 EDA also highlights the importance of understanding the physical properties of asteroids in order to accurately model the Yarkovsky effect. An asteroid's shape size and surface composition all influence how it absorbs and radiates heat, which in turn affects how strongly the Yarkovsky effect influences its orbit. For example, an asteroid with a highly irregular shape, or a surface that reflects heat differently from other surfaces, will experience a more pronounced Yarkovsky effect. In contrast, a smooth spherical asteroid with a more uniform surface will experience a weaker Yarkovsky force. These variations in surface characteristics make it challenging to predict the exact influence of the Yarkovsky effect on an asteroid's orbit, especially for objects that have not been closely studied. This is where detailed observations and advanced modelling techniques come into play. By analysing the physical properties of an asteroid and tracking its movement over time, scientists can develop more accurate predictions of how the Yarkovsky effect will influence its orbit. The study of IDA and other asteroids has helped refine the models used to predict the long-term motion of these objects. This predictive capability is crucial for assessing the potential threat posed by near-Earth objects, and for developing strategies to mitigate any risks they may present. While 243 EDA is not a direct threat to Earth, its case illustrates how the Yarkovsky effect can alter the orbits of asteroids over time. The knowledge gained from studying objects like EDA has broader implications for planetary defense and our understanding of the solar system. Over millions of years, the Yarkovsky effect in conjunction with gravitational forces will continue to shape the orbits of asteroids and other small bodies. By studying these objects and refining our models of their motion, we can gain a deeper understanding of the forces that govern the solar system and develop strategies to protect Earth from potential asteroid impacts. The Yarkovsky effect, while often too subtle to notice in the short term, carries with it the potential for profound long-term consequences. The small, seemingly insignificant changes it induces in the motion of asteroids and other celestial bodies, when accumulated over millions or even billions of years, can result in dramatic shifts in their orbits. These shifts may not be noticeable to the casual observer, but over vast timescales, they have the power to alter the trajectories of asteroids, comets, and other small bodies in space, with potentially catastrophic effects. The Yarkovsky effect works quietly in the background, exerting a continuous gentle force on the objects it influences. The heat absorbed by an asteroid from the Sun is emitted as thermal radiation during its rotation, creating a force that pushes the object ever so slightly. While this force is infinitesimally small on a daily basis, it is persistent, building up over time to produce a significant shift in the asteroid's orbit. This process is similar to how the steady wear of wind and water shapes mountains over millennia. In the case of asteroids, the accumulation of small pushes caused by the Yarkovsky effect over millions of years can lead to an orbital change that might not have been anticipated based on gravitational influences alone. Over time, even the tiniest shift in an asteroid's orbit can bring it closer to Earth or send it on a path that intersects with another planet or object. The gradual build-up of these small changes is a reminder that small forces can have large consequences in the grand scale of the universe. Though an individual change may seem inconsequential over billions of years, these subtle forces can accumulate to produce significant alterations in an object's path. The potential consequences of these changes are especially important when considering the potential impact of near-Earth objects. While the likelihood of an asteroid colliding with Earth is low, the fact that small shifts in their orbits can gradually bring them closer to our planet is a reminder of the dynamic and ever-changing nature of the solar system. The Yarkovsky effect is not the only factor that influences the movement of asteroids. Gravitational interactions with planets and other objects in the solar system also play a role in shaping their orbits. However, the Yarkovsky effect adds a layer of complexity to our understanding of how asteroids move through space. As scientists track the movement of asteroids over long periods of time, they must account for both the gravitational forces at play and the subtle influences of the Yarkovsky effect. This dual influence complicates the prediction of an asteroid's future path, as the small shifts caused by the Yarkovsky effect may not be easily detectable in the short term. Over the course of millions of years, however, these shifts can add up, resulting in a trajectory that is completely different from what might have been predicted based on gravitational interactions alone. One of the key aspects of the Yarkovsky effect is that it is a continuous, ever-present force. Unlike gravitational interactions, which occur in discrete events as objects pass through one another's gravitational fields, the Yarkovsky effect is ongoing. The heat absorbed by an asteroid from the Sun is radiated back into space as it rotates, creating a constant incremental push. This push is not something that occurs once or twice, but rather a continuous influence that shapes the asteroid's orbit over time. This persistent effect means that even if an asteroid's movement is not immediately impacted by the Yarkovsky effect over long periods, it will accumulate enough of a shift to alter the object's trajectory. The role of the Yarkovsky effect in shaping the fate of asteroids is most apparent when considering the potential for asteroid impacts. While large asteroids are less susceptible to the Yarkovsky effect due to their greater mass and slower rotation, smaller asteroids are much more sensitive. A small asteroid which might seem inconsequential in the context of the solar system can be gradually pushed into an orbit that brings it closer to Earth. Over millions of years, this tiny force can cause a significant shift in the asteroid's path, potentially leading to a collision with our planet. The fact that the Yarkovsky effect can gradually alter an asteroid's orbit makes it an important consideration for planetary defense. While the chances of an asteroid collision with Earth may seem remote, the potential consequences of such an event are too great to ignore. The continuous influence of the Yarkovsky effect on small bodies in the solar system means that the risks posed by near-Earth objects are not static, they evolve over time. As scientists continue to monitor the movement of asteroids and other small bodies, they must account for the long-term effects of the Yarkovsky effect in their predictions. A small gradual shift in an asteroid's orbit could over time bring it into a collision course with Earth or another planet. This is why understanding the Yarkovsky effect is critical to the study of planetary defense. While small, the changes in an asteroid's path caused by the Yarkovsky effect can accumulate to the point where they influence the object's interaction with other bodies in the solar system. A collision with Earth, though improbable in the short term, becomes more likely when considering the long-term influence of this subtle force. The Yarkovsky effect is a force that shapes the motion of asteroids and other small bodies in the solar system, guiding them through space with a quiet, steady hand. Though it may not be immediately apparent, the effect of this tiny force builds over time, altering the paths of celestial bodies in ways that might not have been anticipated based on gravitational influences alone. The Yarkovsky effect reminds us that even small changes, when accumulated over vast timescales, can lead to big consequences. It is a reminder that the universe is a dynamic, ever-changing place where the smallest forces can have significant impacts on the paths of worlds. The subtle yet persistent influence of the Yarkovsky effect plays a crucial role in understanding the movement of asteroids and other near-Earth objects (NEOs). While many celestial bodies in the solar system follow predictable paths determined by gravity, the Yarkovsky effect introduces a layer of complexity, especially for small bodies. It is in this complexity that the significance of the Yarkovsky effect becomes clear, particularly in the context of planetary defense. While the Yarkovsky effect is a relatively small force, it has the potential to slowly but steadily alter the orbits of asteroids and comets over long timescales. This shift may seem insignificant on a short-term scale, but when accumulated over millions of years, the effect can lead to an asteroid's orbit crossing Earth's path, resulting in a potential collision. This makes the Yarkovsky effect a key factor in assessing the risks posed by near-Earth objects and understanding how they may evolve over time. Planetary defense initiatives focus on identifying and tracking NEOs that may pose a threat to Earth. While the vast majority of these objects follow stable orbits that pose no immediate danger, some are more unpredictable, especially those that are subject to the Yarkovsky effect. This is because even small changes in an asteroid's trajectory over extended periods can bring it closer to Earth, or change its orbital dynamics enough to intersect with our planet's orbit. The primary challenge for planetary defense is predicting the long-term movement of these objects. NEOs are not static. Their orbits are constantly evolving, influenced by gravitational forces from planets, the Sun's radiation pressure, and in many cases the Yarkovsky effect. As the Yarkovsky effect operates on timescales that span millions of years, scientists must factor in the gradual shifts it induces in an object's orbit when assessing the potential risk it poses. This means that an asteroid which currently poses no threat could, over the course of centuries or millennia, drift into an orbit that brings it into Earth's path. The Yarkovsky effect's long-term influence can also be amplified when combined with other forces. For example, gravitational interactions between asteroids and larger planets, especially Jupiter, can create resonances that accentuate the Yarkovsky effect's impact. This combination of forces can lead to more pronounced orbital shifts, increasing the likelihood of an asteroid being deflected into an orbit that crosses Earth's trajectory. It is these long-term compounded effects that make planetary defense so challenging. While scientists have developed strategies for tracking NEOs, predicting their movements requires an understanding of all the forces acting upon them, including the Yarkovsky effect. The ability to predict how an asteroid's orbit will change over time is crucial for devising potential deflection strategies should a collision become imminent. One of the key methods for mitigating the risk posed by an asteroid on a collision course with Earth is to deflect its path. To do this, scientists must first accurately predict the object's future trajectory, taking into account both the gravitational forces and the Yarkovsky effect. By using telescopes, radar, and other observational tools, scientists can track the movement of NEOs with remarkable precision. However, even the most sophisticated tracking methods are not enough to predict the Yarkovsky effect with absolute certainty. The effect is highly dependent on an asteroid's rotation shape, surface composition, and other factors that can be difficult to measure accurately. This introduces a level of uncertainty into predictions about an asteroid's future orbit, which can complicate efforts to plan a deflection mission. Even with these uncertainties, understanding the Yarkovsky effect allows scientists to develop better models of asteroid motion. By simulating the potential impacts of the Yarkovsky effect on an asteroid's orbit, scientists can gain insights into the possible outcomes and make informed decisions about how to address the threat. These simulations can also help determine the most effective method for deflecting an asteroid, whether through kinetic impactors, gravity tractors, or other techniques. While the Yarkovsky effect may not be the only force acting on a NEO, it is one that must be considered in any planetary defense strategy. The force is small, but its cumulative impact over time can make a significant difference in an asteroid's trajectory. Even minor shifts in the orbit of a large asteroid could result in a collision with Earth, and understanding the Yarkovsky effect is essential for accurately predicting these shifts. As we continue to study the dynamics of NEOs, the role of the Yarkovsky effect will become more apparent. Improved observation techniques, along with advances in modelling, will enable scientists to track the movements of asteroids with greater accuracy, including accounting for the Yarkovsky effect's influence on their orbits. This improved understanding will be crucial for planetary defense efforts, as it will allow us to better predict the potential risks posed by NEOs and develop more effective strategies for mitigating those risks. The Yarkovsky effect also has implications for the future of space exploration. As we look towards sending missions to asteroids, Understanding how the Yarkovsky effect influences their motion will be essential for planning successful missions. Whether it's mining asteroids for resources, studying their composition, or using them as stepping stones for future space exploration, the impact of the Yarkovsky effect must be considered in the planning stages. Understanding how small forces like the Yarkovsky effect can alter the paths of asteroids and comets provides valuable insights into the dynamic nature of the solar system. It highlights the importance of tracking these small bodies not just for planetary defense but for exploring and utilizing the solar system. As we continue to monitor NEOs and improve our predictive models, the role of the Yarkovsky effect will become an increasingly important part of our understanding of how small forces can shape the future of the solar system. By studying this phenomenon, we gain not only the tools to protect Earth from potential threats, but also a deeper appreciation for the complex forces that govern the motion of celestial bodies. The Yarkovsky effect, as subtle as it is persistent, holds the potential to alter the fate of asteroids, comets, and other small bodies in the solar system. Over time, the slow but steady push caused by the thermal recoil can change the path of a celestial object in ways that were previously unimaginable. This phenomenon has profound implications not only for our understanding of space dynamics, but also for the possibilities of altering the orbits of asteroids intentionally using our growing knowledge of the Yarkovsky effect to guide planetary defense efforts. The notion of altering an asteroid's orbit may seem like science fiction, but the Yarkovsky effect provides a real measurable force that could potentially be harnessed. For many asteroids, this tiny force is enough to push them into new orbits, and with the right conditions, it may be possible to accelerate or decelerate this effect, nudging an asteroid in a desired direction. By understanding the specific parameters that influence the Yarkovsky effect, such as an asteroid's size, rotation, surface composition, and its position relative to the Sun, scientists can begin to develop strategies for intentionally altering the orbit of a celestial body. This idea, known as asteroid deflection, has gained increasing attention in the context of planetary defense. While the likelihood of an asteroid striking Earth in the near future remains small, the potential consequences of such an event are catastrophic, making it crucial to explore every avenue for mitigating the threat. One proposed method for asteroid deflection involves using the Yarkovsky effect itself. By altering an asteroid's surface properties, scientists could theoretically increase or decrease its thermal emission, thus changing the amount of force acting on the object. For example, if the surface of an asteroid were to be altered in a way that increased its reflectivity, it could reduce the amount of heat absorbed during the day, thereby weakening the Yarkovsky effect. On the other hand, by darkening the surface, we could increase the heat absorption, amplifying the thermal force and speeding up the movement of the asteroid. Such a strategy would require precise knowledge of the asteroid's physical properties, as well as a thorough understanding of how those properties affect the Yarkovsky effect. The concept of altering an asteroid's orbit using the Yarkovsky effect is still in the realm of theoretical research, but it demonstrates how understanding this subtle force could lead to groundbreaking advances in planetary defense. In addition to surface manipulation, other techniques could be used to enhance or counteract the Yarkovsky effect. One such method involves using a spacecraft to push on the asteroid using a technique known as a kinetic impactor. A spacecraft could be directed to collide with an asteroid, transferring momentum and altering its trajectory. While the Yarkovsky effect would still be at play, the added force from the spacecraft would result in a more immediate and measurable change in the asteroid's orbit. Another potential strategy involves using a gravity tractor, a spacecraft that would fly near the asteroid and use its gravitational pull to gradually shift the asteroid's path. This technique would require a long-term commitment, as the force exerted by the spacecraft would be small but consistent, much like the Yarkovsky effect itself. The key to any successful asteroid deflection strategy lies in the ability to predict the object's orbit over long timescales, and to account for the various forces acting upon it, including the Yarkovsky effect. By accurately modelling the effect of small forces over millions of years, scientists can develop the necessary tools and techniques to make adjustments to an asteroid's path. The possibility of altering the orbit of an asteroid brings with it a sense of both wonder and responsibility. As we learn more about the Yarkovsky effect, the potential to guide the movement of these small celestial bodies becomes more tangible. However, the path to achieving this level of control is not without its challenges. Predicting the Yarkovsky effect's long-term influence on an asteroid's orbit requires advanced models that account for a wide range of variables. The irregular shapes of asteroids, their varying rotation rates, and the diversity of surface properties all complicate the process of modelling their behaviour. Furthermore, any effort to alter an asteroid's orbit would require precise execution. Even a slight miscalculation in the direction or magnitude of a deflection attempt could result in unintended consequences such as a collision with Earth or another celestial body. Despite these challenges, the concept of manipulating the Yarkovsky effect to redirect asteroids remains an area of active research, and with continued advancements in technology, it may one day be possible to implement such strategies. Beyond planetary defense, the understanding of the Yarkovsky effect also has implications for the future of space exploration. As we look to explore asteroids for scientific study or resource extraction, it is important to consider how the Yarkovsky effect may influence the orbits of these bodies. Asteroids are not stationary objects, they are constantly changing their paths, and the Yarkovsky effect is a key factor in these changes. If we plan to land on an asteroid or extract resources from its surface, we must account for the ways in which its orbit may shift over time. Understanding how small forces like the Yarkovsky effect operate will be essential for the success of future space missions. One promising area of exploration involves using asteroids as stepping stones for further space exploration. Asteroids, particularly those in the asteroid belt, contain valuable resources such as metals, water, and other materials that could be used for fuel or construction in space. By using the Yarkovsky effect to guide asteroids into more accessible orbits, we could create a network of resources that could support future missions to the Moon, Mars, and beyond. Such an endeavour would require a deep understanding of how to manipulate the paths of asteroids and the forces that influence them. The Yarkovsky effect in this context becomes not just a force that can threaten Earth, but also one that can enable humanity to explore and utilise the solar system in ways previously thought impossible. As we continue to learn more about the Yarkovsky effect, the role it plays in shaping the motion of celestial bodies becomes clearer. Whether we use this knowledge to defend Earth from asteroid impacts, guide the movement of asteroids for exploration, or even alter the orbits of asteroids to enhance resource extraction, the Yarkovsky effect will be a key factor in humanity's future in space. The potential to shape the destiny of asteroids, guided by a force that has remained largely invisible, brings us closer to the realization that even the smallest forces can have the most significant impact on the future of the solar system. The study of the Yarkovsky effect is a relatively recent development in the field of planetary science, and over the past few decades our understanding of this phenomenon has evolved significantly. What was once a theoretical concept has now become a well-documented and observable force that plays a crucial role in the movement of asteroids, comets, and other small celestial bodies. As the science behind the Yarkovsky effect continues to evolve, so too does our ability to predict its influence on the orbits of objects in the solar system. The journey of understanding the Yarkovsky effect began in the late 19th century, when scientists first recognized the potential for heat to influence the motion of small bodies in space. In the early 1900s, the Russian engineer Ivan Yarkovsky proposed that the rotation of an object and the way it absorbs and radiates heat could result in a small force that gradually altered the object's orbit. However, at the time, his ideas were met with skepticism, and the Yarkovsky effect was largely ignored for much of the 20th century. It wasn't until the advent of more advanced observational technologies, such as radar and space-based telescopes, that the Yarkovsky effect began to gain more attention. The breakthrough came when scientists noticed that the orbits of certain asteroids were not behaving as predicted, based on gravitational forces alone. Instead, these asteroids were shifting in ways that could only be explained by the influence of the Yarkovsky effect. With the increased precision of measurements, astronomers were able to detect small deviations in the orbits of asteroids, which when accounted for revealed the long-term effects of the Yarkovsky force. The development of radar technology allowed scientists to track the position and velocity of asteroids with unprecedented accuracy, making it possible to detect the tiny shifts caused by the Yarkovsky effect. Radar observations of asteroids such as 2443 Ida and 162173 Ryugu helped confirm that the Yarkovsky effect was indeed influencing their orbits. These observations provided concrete evidence that the effect was real and measurable, adding weight to the theories proposed by Yarkovsky over a century earlier. In addition to radar, optical telescopes also played a key role in advancing our understanding of the Yarkovsky effect. Telescopic observations allow astronomers to track the position of asteroids and comets over long periods, providing valuable data on their motion and rotation. By measuring the brightness variations of asteroids as they rotate, scientists can estimate the rotation rates and surface properties of these objects, which are critical factors in determining how the Yarkovsky effect will influence their orbits. The combination of radar and optical observations, along with increasingly sophisticated computer models, has allowed scientists to build more accurate models of asteroid behavior. These models take into account not just the gravitational forces acting on an asteroid, but also the Yarkovsky effect and other factors that influence its motion. By simulating the movement of asteroids over long periods of time, astronomers can predict how small forces like the Yarkovsky effect will accumulate, altering the object's orbit in ways that would not be immediately obvious. One of the challenges of studying the Yarkovsky effect is the complexity of the factors involved. The rotation rate, shape, size, and surface composition of an asteroid all influence the way it absorbs and radiates heat, making it difficult to predict exactly how the Yarkovsky effect will manifest in any given object. For example, asteroids with irregular shapes or varying surface textures experience uneven heat distribution, which amplifies the Yarkovsky force. In contrast, asteroids with more spherical shapes and smooth surfaces are less susceptible to the Yarkovsky effect. Additionally, the distance between the asteroid and the Sun plays a role in how much heat is absorbed, with objects closer to the Sun experiencing a stronger thermal force. These complexities make it challenging to create a one-size-fits-all model for predicting the Yarkovsky effect's influence. Nevertheless, advancements in computational modeling and observational techniques have allowed scientists to make significant strides in understanding and predicting the behavior of asteroids. As our models become more refined, we are able to predict with greater accuracy how the Yarkovsky effect will influence the orbits of asteroids and other small bodies. This ability to predict the long-term movement of asteroids is crucial, not only for scientific exploration, but also for planetary defense. The more accurately we can predict how asteroids will move, the better equipped we will be to prevent a potential collision with Earth. The evolving science behind the Yarkovsky effect is not limited to our understanding of small bodies in the solar system. As we continue to study these objects, we gain insights into the broader dynamics of the solar system, including the role of small forces in shaping planetary and lunar orbits. The Yarkovsky effect may be small in comparison to other forces, but its impact over long periods of time is undeniable. The slow, persistent shifts in the orbits of asteroids and comets are a reminder of how even the tiniest forces can have large-scale effects when given enough time. The study of the Yarkovsky effect is an example of how small, seemingly inconsequential phenomena can shape the evolution of the solar system. By continuing to study and refine our understanding of the Yarkovsky effect, we are unlocking new insights into the motion of celestial bodies and the forces that govern the cosmos. As we continue to develop new observational techniques and improve our modelling capabilities, our ability to track and predict the movements of asteroids and comets will only grow stronger. This evolving science holds great promise for the future, not just in terms of planetary defense, but in our broader understanding of the dynamic and ever-changing nature of the solar system. The Yarkovsky effect is just one example of how small forces acting over long periods of time can reshape the cosmos. As we move farther from the Sun, the influence of the Yarkovsky effect on celestial bodies diminishes, but it does not disappear entirely. The small forces that act on asteroids and comets closer to the Sun continue to affect these objects as they travel outward into the colder, darker regions of the solar system. Beyond the main asteroid belt lies the Kuiper belt, a vast region populated by icy bodies, comets, and dwarf planets. It is here on the fringes of the solar system that the Yarkovsky effect's impact is less immediately obvious, yet it still plays a role in the long-term evolution of these distant objects. While objects in the outer reaches of the solar system are subject to less intense solar radiation, they still experience the Yarkovsky effect. The key difference between objects near the Sun and those farther out is the amount of heat they absorb. As the distance from the Sun increases, the intensity of solar radiation decreases, and objects in these regions absorb less heat overall. Consequently, the Yarkovsky effect is less pronounced in the Kuiper belt and the Oort cloud, the farthest region of the solar system. However, even though the force is weaker at these distances, it still contributes to the subtle drift of these objects' orbits over long timescales. This is especially true for the smaller, irregularly shaped bodies that populate these outer regions, as their uneven surfaces and rapid rotations make them more susceptible to the Yarkovsky effect. While gravitational forces dominate the motion of objects in these distant regions, the Yarkovsky effect is an additional force that can slowly change the trajectories of icy comets and trans-Neptunian objects. These bodies, which are often highly eccentric in their orbits, can experience gradual shifts due to the Yarkovsky effect nudging them into different paths. The effect may be subtle, but over millions or billions of years, these small changes can accumulate, influencing the orbits of comets and objects in the Kuiper belt and Oort cloud, eventually sending them on trajectories that bring them closer to the inner solar system. The role of the Yarkovsky effect in shaping the orbits of these distant bodies becomes even more significant when considering the interactions between the Sun's radiation and the gravitational influences of the giant planets. Jupiter, with its immense gravitational pull, can alter the orbits of objects in the outer solar system, redirecting their paths and sometimes amplifying the effects of the Yarkovsky force. As these objects travel toward the inner solar system, the cumulative effect of the Yarkovsky force can cause them to become more eccentric, bringing them into close proximity with the planets. This process is especially important for comets, which often have highly elliptical orbits that take them from the distant reaches of the solar system to the vicinity of the Sun. When comets pass through the inner solar system, they are subjected to intense solar radiation, which increases the Yarkovsky effect's influence. Over time, the repeated exposure to this radiation can cause comets to move into different orbits, sometimes shifting their trajectories enough to bring them into conflict with the inner planets, including Earth. While the overall likelihood of an asteroid or comet from the outer solar system colliding with Earth remains low, the slow accumulation of changes in their orbits due to the Yarkovsky effect makes it a factor that cannot be ignored. The outer regions of the solar system, though sparsely populated with objects, contain a significant number of bodies that are still in motion, influenced by small forces like the Yarkovsky effect. These bodies, while far from the Sun, continue to drift and evolve, propelled by thermal forces that gradually alter their orbits. In the Oort cloud, for instance, the Yarkovsky effect can influence the motion of icy bodies, even those that are located far beyond the orbit of Pluto. The Oort cloud, a distant spherical region surrounding the solar system, is home to billions of icy objects that are often on long elliptical orbits. Some of these bodies are periodically disturbed by the gravitational influence of nearby stars or galactic forces, sending them on a path that brings them closer to the inner solar system. During these interactions, the Yarkovsky effect can play a role in altering the object's orbit, contributing to the long-term evolution of the body's path through space. As the science of planetary defense continues to evolve, it is essential to consider not only the objects in the asteroid belt, but also those on the fringes of the solar system. The Yarkovsky effect's ability to subtly alter the orbits of objects in the outer regions of the solar system may one day have significant implications for planetary defense, especially as our ability to track and predict the movement of these objects improves. While these bodies are currently far from Earth, the long-term drift caused by the Yarkovsky effect could bring them closer to the inner solar system, making it more difficult to predict their trajectories. As we expand our search for near-Earth objects, we must account for the influence of the Yarkovsky effect, not just on the asteroids we are most familiar with, but also on the comets and icy bodies in the outer reaches of the solar system. The slow but steady push of the Yarkovsky effect, combined with gravitational interactions and other forces, could one day bring an object from the outer solar system into a collision course with Earth. By understanding how these forces work, we can develop better methods for predicting the long-term movement of distant objects, ensuring that we are prepared for any potential risks. The study of the Yarkovsky effect on objects in the outer solar system also has implications for our broader understanding of the solar system's formation and evolution. As we observe how small forces like the Yarkovsky effect influence the motion of bodies in the distant reaches of the solar system, we gain insights into the processes that have shaped the current structure of our solar system. The outer regions, where objects remain largely undisturbed for billions of years, hold clues to the early history of the solar system and the forces that have guided its evolution. The Yarkovsky effect, though small in comparison to gravitational forces, plays a crucial role in the ongoing transformation of the solar system. By understanding how it operates in the outer reaches of the solar system, we can gain a deeper appreciation for the delicate balance of forces that govern the movement of bodies in space. The Yarkovsky effect is a small force, yet it holds the remarkable potential to influence the trajectories of celestial bodies over vast timescales. The small shifts it creates in an asteroid's orbit, often imperceptible in the short term, accumulate over millions or billions of years, propelling these bodies across the solar system in ways that can be far-reaching. These tiny pushes, when combined with the other forces acting on asteroids, comets, and other small bodies, can result in dramatic changes to their orbits, altering the paths of objects that were once thought to be on predictable courses. What makes the Yarkovsky effect especially significant is its persistence. It operates continuously, creating a slow but steady force that pushes an asteroid ever so slightly in the direction of its rotation. While the force is minuscule, its cumulative effect over millions of years can result in a significant change in an asteroid's trajectory. Over time, an asteroid's orbit can be altered enough to send it into different regions of the solar system, sometimes even bringing it into contact with Earth or other planets. This gradual shift highlights the importance of considering the Yarkovsky effect when studying the motion of small bodies in space. The fact that such a small force can have a significant impact over vast timescales is a reminder of how even the tiniest influences can shape the course of events in the cosmos. One of the most striking aspects of the Yarkovsky effect is its ability to affect the motion of objects that are in many cases too small to be significantly influenced by gravitational forces alone. While gravity is the dominant force controlling the motion of planets and large moons, smaller objects like asteroids, comets, and trans-Neptunian bodies are more susceptible to the Yarkovsky effect because of their relatively low mass and irregular shapes. This makes the Yarkovsky effect particularly important for understanding the long-term evolution of these small bodies. While gravitational interactions with other objects in the solar system certainly play a role in the motion of asteroids, the Yarkovsky effect provides an additional force that can slowly but persistently alter their orbits. The influence of the Yarkovsky effect is especially apparent when considering the movement of asteroids across the solar system. Asteroids that once seemed locked in stable orbits governed by the gravitational forces of the Sun and the planets are slowly being nudged by the Yarkovsky effect into new paths. Over the course of millions of years, this tiny force can gradually alter the asteroid's orbit, causing it to move closer to Earth or to cross the orbits of other planets. The cumulative effect of this small consistent force is that asteroids and comets are constantly changing their trajectories, even if those changes are not immediately apparent. For an individual asteroid, the Yarkovsky effect may seem insignificant at first. The force is so small that it cannot produce an immediate change in the asteroid's motion. However, when viewed over long timescales, the effect becomes apparent. Over the course of millions of years, even a tiny change in the asteroid's orbit can result in a shift that alters its position relative to other objects in the solar system. These small gradual changes can eventually lead to a collision or a near miss with Earth, or they may redirect the asteroid to a completely different orbit where it remains for billions of years. The long-term effects of the Yarkovsky effect are felt most acutely in the region of the solar system, where asteroids are most abundant, the asteroid belt between Mars and Jupiter. This region is home to a vast number of objects ranging from tiny pebbles to large bodies several hundred kilometers in diameter. It is in this region that the Yarkovsky effect can most significantly alter the orbits of objects, slowly pushing them into new trajectories that bring them closer to the inner solar system or farther out into the outer reaches of space. The same principles that apply to asteroids in the asteroid belt also apply to bodies in the Kuiper belt and the Oort cloud. These regions located at the outer edges of the solar system contain many icy bodies and comets that, like asteroids, are subject to the Yarkovsky effect. As these objects travel through the solar system, the Yarkovsky effect pushes them ever so slightly, gradually altering their paths. Over millions of years, these subtle changes can accumulate, moving the objects into different orbits and potentially sending them toward the inner solar system. The small forces at play in the outer regions of the solar system are just as important as those in the inner solar system. Over long timescales, the Yarkovsky effect can push objects from the outer reaches of the solar system into the vicinity of Earth or other planets. As these objects travel toward the inner solar system, they are exposed to stronger solar radiation, which amplifies the Yarkovsky effect. The combination of this thermal force with gravitational influences can lead to significant changes in their orbits. The journey of these objects influenced by the Yarkovsky effect may take them on a vast winding path through the solar system. It's important to remember that while the Yarkovsky effect may be small, its cumulative impact is vast. Over time, the tiny push from this force can lead to large-scale changes in the orbits of asteroids, comets, and other small bodies. These objects are not static. They are constantly being nudged by the Yarkovsky effect, slowly drifting across the solar system. This ongoing journey shaped by small forces underscores the dynamic and ever-changing nature of the solar system. As we look to the future of planetary defense and space exploration, the Yarkovsky effect reminds us that even the smallest forces can have significant consequences. It serves as a reminder that the motion of celestial bodies is influenced by many factors, both large and small, and that even a tiny force like the Yarkovsky effect can alter the destiny of an asteroid or comet. This tiny push can send objects on a journey that takes them across the solar system, ultimately changing their position in relation to Earth or other planets. Understanding the Yarkovsky effect allows us to appreciate the intricate dance of forces that govern the motion of celestial bodies, and it reminds us that the seemingly insignificant can have far-reaching consequences. The Yarkovsky effect is intrinsically tied to the interaction between a celestial body and solar radiation. The Sun, the most powerful source of energy in the solar system, plays a pivotal role in shaping the movement of asteroids, comets, and other small bodies in space. The way these objects absorb, retain, and radiate heat from the Sun directly affects how the Yarkovsky effect operates. The force is generated by the uneven distribution of thermal radiation as a rotating body absorbs solar heat and then re-emits it over time. This uneven release of thermal energy, caused by a combination of the body's rotation and its interaction with the Sun's energy, gives rise to a small but significant push. The role of solar radiation in this process cannot be overstated. The Sun's radiation is the primary driver of the Yarkovsky effect, as it determines how much heat an object absorbs and how it re-emits that energy. When a celestial body, such as an asteroid, is illuminated by the Sun, the side facing the Sun absorbs radiation and becomes warmer. As the body rotates, the side that was previously in sunlight moves into shadow, and it begins to cool down, radiating the stored heat back into space. This process is not uniform. The heat is not emitted evenly in all directions. Instead, it is emitted more strongly from the side opposite the direction of the object's rotation. This discrepancy in the thermal radiation leads to a net force that pushes the object in the direction of its rotation. The more quickly an object rotates, the more rapidly the heat is re-emitted and the greater the resulting force. As such, the speed of rotation plays a significant role in determining how strongly the Yarkovsky effect influences a given object. A faster rotating asteroid will experience a more pronounced effect because the heat is radiated more quickly, intensifying the force and its impact on the object's trajectory. On the other hand, A slower rotating body will radiate heat more slowly, resulting in a weaker Yarkovsky force. The amount of heat absorbed by an object is also a crucial factor in the strength of the Yarkovsky effect. An asteroid's surface properties such as its albedo or reflectivity determine how much solar radiation is absorbed versus reflected. Darker bodies with lower albedo absorb more solar radiation than lighter bodies, making them more susceptible to the Yarkovsky effect. In contrast, asteroids with higher albedos, such as those that are lighter in color, reflect a larger portion of the sun's radiation, which reduces the amount of heat they absorb and weakens the Yarkovsky effect. The surface composition of an asteroid can further influence how it absorbs and radiates heat. Some materials, such as metals, have higher thermal conductivities, meaning they can transfer heat more efficiently across the object's surface. This can lead to more uniform heat distribution and a weaker Yarkovsky effect as the thermal radiation is less uneven. Conversely, asteroids composed of porous or less thermally conductive materials may experience a more pronounced Yarkovsky effect because the heat remains more concentrated in specific regions of the object, leading to greater differential radiation. The intensity of solar radiation itself also plays a role in the Yarkovsky effect. As a celestial body moves farther from the Sun, the intensity of solar radiation decreases. Objects in the outer solar system, such as those in the Kuiper belt and the Oort cloud, receive much less solar energy than those closer to the Sun. As a result, the Yarkovsky effect is weaker for these distant objects. However, even in the coldest, darkest regions of the solar system, the effect is not entirely absent. Over long periods, these small gradual shifts caused by the Yarkovsky effect can accumulate, potentially altering the orbits of comets, asteroids, and other bodies. For objects in the inner solar system where solar radiation is more intense, the Yarkovsky effect plays a more significant role in altering their trajectories. In particular, objects that orbit close to the Sun, such as those in the asteroid belt or the near-Earth asteroid population, are subject to strong solar radiation. The Yarkovsky effect in these regions can cause asteroids to move into new orbits, sometimes shifting their paths into the inner solar system or altering their trajectories to cross Earth's orbit. For planetary defense understanding, the Yarkovsky effect is essential because it reveals that asteroids and comets are not always on predictable paths. Even if an asteroid's orbit appears stable in the short term, the cumulative effects of solar radiation and thermal re-emission can cause it to change its trajectory over time. While the Yarkovsky effect is generally a slow process over millions of years, it can lead to a dramatic shift in an object's orbit. This makes it important to account for the Yarkovsky effect when assessing the long-term risk of asteroid impacts on Earth. The role of solar radiation extends beyond just the Yarkovsky effect. It also plays a role in the overall energy balance of the solar system, affecting the motion and behavior of comets, asteroids, and even planets. The Sun's radiation pressure, which pushes against objects in space, can also influence the orbits of smaller bodies. While this force is much weaker than gravity, it adds another layer of complexity to the dynamics of the solar system. Together with the Yarkovsky effect, solar radiation helps shape the movement of small bodies in space, and this influence extends to the farthest reaches of the solar system. Understanding the ways in which solar radiation interacts with the orbits of asteroids and comets is crucial for predicting their long-term motion. As we continue to observe and study asteroids and comets, the role of solar radiation in shaping their trajectories will only become clearer. The Yarkovsky effect, driven by the Sun's radiation, is a reminder of how small forces can have large-scale impacts over time. In the end, the tiny thermal pushes created by solar radiation, when accumulated over vast stretches of time, can lead to significant changes in the paths of celestial bodies. The Yarkovsky effect, while a subtle force in the short term, plays an important role in the long-term evolution of our solar system. As small bodies, such as asteroids and comets, drift through the vast expanse of space, the cumulative influence of the Yarkovsky effect slowly alters their orbits, gradually changing their paths and potentially even their interactions with other objects in the solar system. Over vast stretches of time, this continuous push leads to a shifting cosmic landscape. It is through these small gradual changes that the solar system as we know it has evolved. Celestial bodies, though often thought of as static in their orbits, are in fact constantly in motion, influenced by the ever-present forces that govern the solar system. The Yarkovsky effect is one of the more subtle yet persistent forces acting on these small bodies, even in regions where gravitational forces are strong, such as the asteroid belt or the near-Earth space. The Yarkovsky effect continues to play a significant role, altering the motion of these objects. This slow, continuous evolution is a fundamental characteristic of the solar system's dynamic nature. The influence of the Yarkovsky effect is not limited to the asteroid belt or near-Earth objects. The solar system, while vast, is filled with small bodies spread across its entire expanse from the distant Oort cloud to the inner reaches of the solar system. While the effect is more pronounced for bodies in the inner solar system where solar radiation is more intense, its influence can be detected in the outer regions as well, albeit to a lesser extent. Even in the cold reaches of the Kuiper belt and Oort cloud, where sunlight is weaker, the Yarkovsky effect still plays a role in altering the orbits of comets and icy bodies. As these bodies travel through the solar system, they gradually experience shifts in their orbits, which can result in dramatic long-term consequences. This process highlights the dynamic and ever-evolving nature of our solar system. The Yarkovsky effect is not the only force at work in shaping the movement of celestial bodies. Gravitational interactions with the Sun and the planets play a significant role in defining the orbits of larger bodies. However, even the largest bodies in the solar system are subject to the same forces, albeit to a lesser degree. The Sun's gravitational pull dominates the motion of the planets, yet the Yarkovsky effect still plays a role in the trajectories of smaller bodies like asteroids, comets, and trans-Neptunian objects. This interplay between different forces is what creates the dynamic and constantly changing nature of the solar system. The Yarkovsky effect also contributes to the ongoing reshaping of the solar system's architecture. Over long periods of time, it alters the distribution of small bodies in the solar system, moving objects from one region to another. Asteroids that once populated the asteroid belt may be pushed into new orbits that bring them closer to Earth or further out into the solar system. Likewise, comets in the outer solar system influenced by the Yarkovsky effect may be nudged toward the inner solar system, where they can become more visible and interact with the gravitational fields of the planets. These small changes may seem insignificant over short timescales, but over the course of millions or billions of years, they can lead to significant shifts in the structure of the solar system. The Yarkovsky effect, therefore, is not just a force that impacts the motion of individual asteroids or comets, it is a force that drives the evolution of the solar system itself. By altering the orbits of small bodies, the Yarkovsky effect reshapes the solar system over long timescales, guiding the movement of objects as they travel through space. The changes driven by this force, while slow and subtle, are a testament to the ongoing transformation of the solar system. Over time, the cumulative influence of the Yarkovsky effect can lead to a reshuffling of the orbits of celestial bodies, potentially causing objects to collide, merge, or move into different regions of space. These changes, though gradual, help shape the solar system into the dynamic system we observe today. The role of the Yarkovsky effect in the solar system's evolution is particularly important when considering the long-term survival of the Earth. While the risk of a catastrophic asteroid collision with Earth in the near future is low, the gradual accumulation of changes caused by the Yarkovsky effect could over millions of years bring an asteroid or comet on a collision course with our planet. Understanding the Yarkovsky effect and its impact on asteroid orbits allows us to predict how these objects might evolve and interact with Earth. This understanding is essential for planetary defense as it helps us assess the potential risks posed by near-Earth objects and develop strategies to mitigate those risks. As we continue to monitor and study asteroids, comets, and other small bodies in the solar system, our understanding of the Yarkovsky effect will deepen. With better observations and more advanced computational models, we will be able to predict the long-term trajectories of these objects with greater precision. This will allow us to anticipate potential threats, track the movement of objects, and develop strategies for deflecting any asteroid that may pose a danger to Earth. The Yarkovsky effect is a force that, while small in its individual influence, plays a significant role in shaping the cosmic evolution of the solar system. By gradually altering the paths of small bodies, it contributes to the dynamic and constantly changing nature of our solar system. This quiet force, which operates over vast timescales, drives the motion of objects across the solar system, subtly nudging them in new directions and ensuring that the solar system remains a place of constant change and evolution. The study of the Yarkovsky effect and its implications for planetary defense is just one example of how understanding the forces at play in the universe can help us better understand the nature of the solar system and our place within it. As we continue to explore the cosmos, the Yarkovsky effect will remain a key factor in shaping the motion of celestial bodies and in the ongoing evolution of our solar system.